This question is kind of a prelude to what we're going to do the next several days. Those of you that may have already started with some of the later assignments, you see maybe a little bit of this in some of those assignments later on, but there will be some additional assignments that we do by hand that focus solely on this, because Math Excel doesn't have a great kind of pool of questions to pull from. So we'll do a lot of worksheets in the coming days. This is asking you, obviously, whenever we start seeing ordered pairs, we need to go to the coordinate plane, right? And start graphing things in the XY axes. And then when we do that, the next thing that should come to mind are three formulas: distance, midpoint, and slope. Okay? And be able to know when and where to use those appropriately. Okay? This one obviously tells you to find distances, right? Or lengths. So that one you're going to use a distance formula. So my suggestion as you're doing these, graph the image. Okay? It doesn't have to be a great graph. It doesn't have to be the scale. Okay? Usually what I do is I say, okay, point A has got to be in the second quadrant. Okay? Or on the axes between the second and third quadrant. Negative 4, 3, or point B, that's got to be in the what? Second quadrant, right? Okay. 0, 5 is on the y-axis in the vertical direction, and 2, 2 is in the first quadrant. So that's really all I do. Okay? I don't really draw things to scale, but I draw the picture so that I can just organize the information that I found, and it provides me insight and reminders of what I need to find to progress and finish the problem. Okay. Without a picture, you're going to do. You can do it if you're a very organized person. You can visualize what's going on without a picture. That's great. But if you don't have a picture, chances are you're going to make a mistake. You're going to leave something out. You're going to forget something. You're going to add something in that you don't need. A picture is a very, very useful tool in this. So, that being said, let me plug these points in. Let's go. Negative 2, 0. Negative 4, 3. 0, 5. And 2, 2. All right, so that's the set of points, and then we're talking about a quadrilateral, so it's a polygon, so go ahead and close it off with segments. And now we're going to start doing the work. Okay, it says find the distance of all four segments here. Okay, so first thing I'm going to do is I'm going to focus on that segment right there. Okay, so I'm going to focus on the blue segment. Remember, distance is a formula that takes your x values, you subtract them and square them, and then you take your y values, you subtract them and square them. It says we subtract your x's, square that quantity, subtract your y's, square that quantity, and then you take a square root of that. Okay? So when I'm doing this problem, I'm trying to find the length of C to B. It's a good idea to label things. Don't just use this formula 4 times and not label anything. You're going to make mistakes doing that. So if I look at B and C, I'm going to subtract the x's. Now, we've talked about this many a times, it does not matter the order that you subtract them. So what is 0 minus negative 4? 0 minus negative 4. It's positive 4, right? And then we're going to square that, right? Okay. So x2 minus x1 gives me the 4. Then we put the square exponent there. So now I'm going to do the same thing with my y. So it's 5 minus 3. 2. And we're going to square that, right? So what is 4 squared? 16, what is 2 squared? 4, what's 16 plus 4? 20. Okay? Now, that is the length of BC. It is root 20. Now, if you type that into Math Excel, you're going to be wrong because Math Excel says simplify your answers, right? Okay? So radical 20 is not a fully simplified radical. Okay? Radical 20 has a perfect square that is residing inside the 20 as a factor. And when we take square roots of things, we want to reduce them. We need to basically divide out all the perfect squares that exist inside that 20. Okay? 20 is called a composite number, right? And numbers that you can find factors for other than one in itself are called composite numbers. Okay? So a couple different ways you can do this. Simplify. You take your 20 and you think about what numbers that are perfect squares that will divide. Okay? And when we mean divided, we say divide it and get a quotient that is a whole number back. Okay? You can obviously think, okay, if we're going to whole number back, then there has to be numbers that are less than 20, right? But the first whole number that I want to get back really would be 2. So then I really only have to look at numbers that are less than half of 20. Okay, so what I always do is I take that number underneath the radical, half it, so I get 10, and now I start dividing 20 by the perfect squares that are less than 10. Well, those are only 4 and 9, right? Does 20 divide by either of those? 20 divides by 4, right? Okay, so I know 20 has a perfect square of 4 residing inside of it, and we need to get rid of that. Okay? So what we can do, if I divide 20 by 4, what are you left with? 5. So root 20 is actually the same thing as the root of 4 times 5, right? Well, there's a little bit of exponent rules that allow this to happen. You guys talked about some exponent rules last year in Algebra 1, but that is something that we're allowed to do. Okay? Maybe if we have time later on, I'll go back through that algebra of why you can take that product underneath one radical and write it as a product of 2 radicals. It's not that difficult, but we are allowed to do that. And now when I see it this way, what can I do with that radical 4? What is that the same as? 2. And then the radical 5 is just radical 5. Radical 5 is not a perfect square, so it stays radical 5. So now BC we write as 2 radical 5. Does that make sense to everybody? There are other approaches, and I don't care which approach you use. Use something that makes sense to you. Sometimes you see, this is kind of the way maybe initially in Algebra 1 you learned it, is you take 20 and you say that's composite, so I know it's divisible by something, and it's divisible by 2, right? If I divide 20 by 2, what are you left with? Left with 10, right? Okay, so we end up stopping at prime numbers. This is referred to as the prime factorization of 20. We then take our 10, because that's composite still, and we start dividing it. Well, what does 10 divide by? 2 and gives me 5. Okay, so 2 is prime, so we stop at that one. Is 5 prime? Yes, we stop at that one. Every single composite number you ever come across can be broken down to a product of prime numbers. Okay? What we're saying here when we do this is that radical 20 is the exact same thing as that radical 2 right there times that radical 2 right there times that radical 5 right there. Is that okay with everybody? Well, when you take a square root times itself, okay, that's this. That's saying radical 2 squared, isn't it? Times radical 5. Well, what's a square root and a power of 2 do to one another? Cancel each other out. And you're left with just 2 radical 5. Okay? So that's another way of doing it, but I think that way obviously is a good technique. It never fails you. However, what happens if that number is not 20, but it's 2,000? Okay? So then your factor tree gets a lot longer, right? I like to use that kind of that division algorithm I explained. I'm taking half of that number and then start dividing by the perfect squares that are less than that, but it's totally up to you. But we got to write it as 2 radical 5. Now, some of you might say, well, my calculator does this for me. Anybody's calculator do that for them? Awesome. You're lucky, right? Guess whose calculator won't do that for you? The one you get on the state test. Okay? Most likely will not, when you type in radical 4 and spit back 2 radical 5. But that's how it'll ask you to answer your question. Does that make sense? Okay, so if you're a person that relies on that, please don't be a person that relies on it because you don't know how to do this. Okay? Because you'll then obviously miss some things on that state test. So now, that's BC. We need to go through and find some other segments, right? So let's go find that one. Make it green. So find the green segment AD. So distance from A to D. Again, it's going to be the exact same distance formula. Okay, you're always coming back up to that formula. So now I'm going to take the x's from A and D and subtract those. So it's 2 minus negative 2. 4. Okay. When we're subtracting things out, the most common wrong answer I get there is 0, right? Okay. If you struggle with the subtracting of negative numbers in your head, write it down. Because then you see the 2 negatives back to back and you know that's addition, right? So you get 4, square that, you get 16. Same thing with your y's. 2 minus 0 is 2. Square that, you get 4, right? Is that still radical 20? Is radical 20 still going to be 2 radical 5? So what does that tell you about the blue side and the green side? They're what's one another? They're congruent. So we have shown that, which is nice. That's part of what is necessary for us to have a parallelogram. The other things we need to find out to have a parallelogram is that the red sides are congruent to one another. So we find those lengths. So we go a distance of, let's go A to B. So I go negative 4 minus negative 2. What's negative 4 minus negative 2? Negative 2. Negative 2 squared is 4, right? What's 3 minus 0? 3 squared is 9. It's going to be a radical 13. What kind of number is 13? What numbers divide 13? There's 2 numbers to divide it. 1 and 13, right? So 13 is a prime number. When a number is only divisible by 1 in itself, it's prime. So there is no perfect square residing inside that, so it's already simplified. Okay. If I find distance C to D, hopefully it ends up being radical 13. 0 minus 2 would be negative 2 squared would give me 4. 5 minus 2 gives me 3. 3 squared would be 9 again. So I do get radical 13 as that length there. So that shows us that the red distances are in fact the same, right? So through the theorem that said if in a quadrilateral both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram, right? Okay. When you get to the end of course exam, okay, and this is something to think about as you progress through this math class and a lot of other math classes as they get more and more difficult, it's not just about calculations. It's just not about computations. They're going to ask you, explain yourself. You did all the work. You provided numerical data. Now write out why you knew to do that, and write out why you know you can make the conclusion that you can make. Okay? It's not enough just to say I've got 2 radical 5, 2 radical 5, radical 13, radical 13. They're going to say, okay, now explain why this is parallelogram. And you state that because there exists a theorem that says when both pairs of opposite both pairs of opposite sides are congruent, then the quadrilateral is parallelogram. Okay? Math is about being able to do the calculations, but knowing the rules and the reasons why you can do those calculations, okay? Or why you need to do those calculations. What's nice then is, obviously, we've just dealt solely with distances, right? Well, if I realize that I just worked with just distances, and then I come back and I look at these slopes, that's 0.5 and that's 0.5, right? Does that make those two parallel? This ends up being negative 1.5 and negative 1.5. Those two are parallel, okay? So when the distances are the same like they were, then automatically the slopes are the same as well. Okay? And the slopes are, I guess, opposite slopes are the same. And that then becomes a parallelogram, or is classified as a parallelogram. Is that something we can do? Now we're going to do a lot of that. Okay, that's going to be the foundation of the next bedroom. Whatever.